Welcome, everyone. Can you hear me? This is kind of loud. Okay. I'm Alex Kontorovich, Heather Macbeth, Antoine Chambarroir. We're really happy to have all of you here. We're very excited. We are delighted. Let me just thank Yuri for encouraging us to put this together, and David Spergel for agreeing to do it, and of course, Christina Darras, who's been tremendous at getting all of you here and housed and all your travel and so on. We're supposed to be about half the size that we are. There was so much demand that I kept begging Christina, can we put one more person in? And she said, the last one, because she knew that I've already asked 20 times, can we get one more person in? So here we are. We're way oversubscribed, but hopefully everybody is comfortable. There's also an overflow room, which will be more useful for the workshop component. So let's just talk down the schedule. So we've prepared for you 3 courses, because there are sort of 3 different subjects in how you want to interact with, well, mathematics in general, but in Lean in particular. So you'll get 2 lectures in analysis, you'll get 2 lectures in algebra number theory, how do you deal with algebraic structures, and 2 lectures in geometry topology, how do those things work in Lean. Now, if you notice, the course is, you basically have, something like 2.5, 3 hours for each of these. So there's going to be an hour of show and tell, by us, followed by, well, a half-hour coffee break, and then an entire hour to just sit and work through the problems. Okay, so in groups, there are a number of Lean experts here who will be floating around, also helping you get Lean installed on your computer. Out of curiosity, how many have Lean installed? We're not going to do it now. We're not going to do it. Yeah. But the vast, a lot of people already have it. We do not assume that you have Lean installed on your computer. We're going to start from the very, very basic ground and work our way up. And we're going to end every day with a little show and tell. So if you found something cool, come and tell us. And at 4 o'clock, we'll have you come up and show us how you solved some problem, what you learned in the process. I think that'll be a useful component of it. There's lunch between noon and 1. I forget what the building is. Oh, just follow the crowd. We'll figure out where we're going. Today, we're going to have a reception at 5 o'clock on the roof. So stick around for that. Some wine and cheese, I'm told. Okay. Did I forget to say anything? We'll get to Zulip. We'll get to code spaces. There's a lot of stuff we still have to tell you about. Right. So let's just Lean, the word Lean means lots of different things to different people. So let me try to clarify. This is sort of the picture in my mind. And by the way, the 3 of us have very different views on these things. So you're going to get 3 very different views on how to use these systems. And it's not that we're a country. This is sort of quasi by design, I think, that we want you to see lots of different viewpoints on how to use these systems. So my viewpoint is that Lean was originally software for code verification. The fact that it proves theorems is like a sideshow, but of course that's become one of the big important uses of it. And the fact that there is software for code verification is a 70-year-old idea. There are lots of other systems, Isabel, Koch, Hall Light, there's a long list of shoulders on which Lean is building on top of. So I want to make sure I mention that. Now, on top of the software that does the theorem proving, if you ever try to prove something formally, if you don't have a library in which to work, it's nearly impossible. So there's this massive, beautiful library called Mathlib, and it's synthesized. The topology library talks to the geometry library. If you want to talk about Lie groups, you need manifolds, you need algebraic structures, you need all kinds of things, and they all interact together. That does not mean if you're doing research or teaching that you need to be necessarily contributing back to Mathlib. And in fact, if you're doing teaching, maybe you don't even want to be using the version of these objects in Mathlib, because the version here is the most general version. Just like we teach, you first teach Riemannian integration, and then you teach Lebesgue integration, and that's okay, and nobody complains about that, right? Even though while you're teaching Riemannian integration, there's a better way to do it. Well, okay, but there's a time for that. So in the same way, with teaching, when we're doing analysis in a few seconds, we're not going to be doing filters, which is the way analysis and limits are implemented. In Mathlib, we're just going to talk about epsilon and delta, and then we'll make our way towards filters. So that's sort of the viewpoint. Any questions so far? Please interrupt at any time. This is a workshop where we're going to have casual conversations. There's nothing formal happening here. So let's talk a little bit about teaching and the way I really like this as potentially a teaching application. I think we're running a lot of experiments. But imagine you're teaching people chess. And so you say, here's how the game went. Knight f3, knight f6, and then there was c4, g6, knight c3, bishop g7. Okay, and this was the game. And look at what happened. Knight a4. Can you believe that? What a crazy move. Okay, so for chess aficionados, yeah, maybe you can make those game boards in your mind. But for the rest of us, myself included, I need to see this. Knight f3, knight f6, c4, and then g6. Okay, just show me the board. Then I can follow the game much more easily. And yet, what we do when we teach mathematics, especially when we teach proofs for the first time, is that first thing. So if you think about when you prove something like square root of 2 is irrational, we all know the proof. Let's say not, then you can write root 2 as a fraction of lowest terms, square both sides, cross multiply, you get to there, so that p is even, so q is even, the contradiction. Every single one of these is an instruction, 1e4, 1e2e5, whatever. It's an instruction, but it doesn't show the game board. Lean shows the game board. Interactive theorem provers show the game board. What does the game board look like in this context? So the theorem is root 2 is not rational. What does that look like in Lean? So there's the rational numbers. This is maybe the ugliest version of how to do this in Lean. You can make it look much nicer, but basically you have the rational numbers and there's a map. Rational numbers are quotients of integers by natural numbers, as opposed to real numbers, which are in Lean, literally equivalence classes of Cauchy sequences of rational numbers. So there's a coercion, there's a map from quotients of integers to equivalence classes of Cauchy sequences, and you need to cast the rational numbers into the reals. And then the range, the image of that map, is how the rational numbers fit inside the real numbers. So root 2 is a real number, and I want to say it's not in the image of the rational numbers when they're mapped into the real numbers. Okay, so that's the game board right now. This means goal. This symbol means goal. So that's the goal. If not, already these first words have changed the game board. We made a move. The game board is now assume the hypothesis that we'll call H, that root 2 is in this image. And then our goal is false, right? We're going to prove this by contradiction. And then if not, then it's equal to a fraction lowest terms. So here's a new hypothesis that we got out of that move. The new hypothesis, there exist integers p and q. Q is not 0, p and q are co-prime, and root 2 is p over q. And the goal is still false. Okay, so you see that at every stage, you're showing them the game board and not just telling them the moves that arise in the game board. You square both sides, and then you cross multiply. So this is sort of, I'm showing you piece by piece what Lean, the information that Lean is keeping track of, and visually putting it there so that you don't have to try to keep track of it in your own mind. We have integers p and q. Q is not 0, p and q are co-prime. P squared is equal to 2q squared, and we're trying to prove contradiction. Okay, does that make sense? So sort of pedagogically, what's happening here is something I think really extraordinary. When you're teaching on a blackboard, you would never write all of these things out. You would never keep drawing the game board in chess, right? The way people teach chess is they hang a game board, but we don't have a way, we haven't figured that out yet. Well, now we have. Lean is that. So A, it would take way too long. B, it's unnecessary. All of you learned to prove theorems without needing that, but it was hard. It's that initial step that we can make a little bit easier for people. By the way, when people get to a high level of chess playing, of course they can think many moves ahead in their mind. So they have to be able to see those chessboards in their mind. Similarly, to do any kind of mathematics at a high level, you do have to develop that game board in your mind, as all of you have already done. But it's that beginning stage. You don't have to do it right from the start. So it's that beginning stage that can be smoothed for teaching. Okay, how are we going to force everyone to use Lean? The analogy is, the answer is you don't. The analogy to me is look at the story of tech. Knuth releases tech in '78. At that time, every mathematician's handwriting papers, handing that paper to a secretary. The secretary in a few weeks or months writes it up, and hopefully what is typeset has some resemblance to what was handwritten. And then, in the early 80s and the mid 80s, Spivak was really pushing for everyone to switch to AMS tech, but almost nobody did. And then by the time LaTeX comes out, it's got tons of macros. People work really, really hard to make it so that an idiot like me can use LaTeX without even thinking about it. Very few people, including my close friends and colleagues, Sarnak, Berg, and Advantage, they're some of the only ones who still don't know how to use LaTeX. Everyone else switched over. By the way, they waited long enough that now the AI can do it for them. They don't have to. They never had to learn how to tech. But I'm not. No one. The young people don't even know how to install Tech Shop or MikTeX or whatever onto their computers. They don't need to. They have Overleaf. It's a free web app. I just go on the app. LaTeX is ready, and then I just use it. And there's tons of macros, so it doesn't bother me that I have to learn $signs, backslashes, and curly brackets. That's a very, very small startup cost for the price that you no longer have to handwrite things and wait for someone else to write it up for you. You just immediately have nicely typeset things. So that's what I call the Knuth constant. It's the time it takes to typeset, even though you have to learn these $signs and backslashes, relative to the amount of time to handwrite. And in the 90s, that went below 1, and everybody switched voluntarily. So the same thing can happen with Lean if we work hard enough at it. So what people speak of usually when it comes to formalization is the so-called De Bruijn constant. De Bruijn imagined, how many lines of formal code does it take to express something relative to the number of lines in a paper. So if you have a 20-page paper and it takes you 4,000 lines of formal code, you can work out what that constant is. And because of the existence now, like in the last maybe 6 months, maybe 3 months of LLMs that can produce lots and lots of lines of code, that is no longer the right proxy. I mean, lines of code were a proxy for time, but that's no longer the right metric to measure things. What I propose instead is the time it takes to formalize a paper, meaning when you're doing research, the amount of time it would take you to do research if you do it in a formal system relative to doing it on paper. So I'm thinking of, as an analytic number theorist myself, I'm thinking of, we write these 100-page papers with lemmas and 30 parameters all over the place. And at the very end, all the parameters have to be in just the right place. And you have to like check and recheck the lemmas because they're technical and it's easy to make, one minus sign kills the whole argument. If I could state my theorems in Lean, and we're not at the point yet where that's possible, but if I could, I would much rather just prove the lemma in Lean formally once. I never have to check it again. Lean is keeping track of the constants. I know I'm not going to make a mistake. And then it's going to speed up eventually, I believe, Lean will speed up the amount of time it takes me to write a mathematical paper. Okay, and that is the point at which the second that ratio goes below 1, everyone's going to switch voluntarily just because we want to do math, and it'll make it easier to do math and keep track of things. Okay, so that's the analog. We also need, in order to get there, we need amazing, efficient libraries. That's where Mathlib comes in. Those of you that want to contribute to Mathlib, that would be great. We also need a lot more automation, a lot of tactics. Week 2, Heather's going to teach us how to do meta-programming in Lean and write those tactics. LLMs help a lot. Some people are opposed to LLMs, and that's perfectly fine too if you don't want to use them. Also, you shouldn't have to download Lean to your hard drive if you don't want to. You shouldn't have to run Tech Shop. You can just run it in the web. That exists already. There's code spaces, Gitpod, et cetera, et cetera. So eventually, everyone will hopefully start working formally, voluntarily, just because it's easier. Okay. We're already now at the stage, and we were not at the stage when we proposed this conference, at least from my viewpoint. We're now at the stage where if you have just a modicum of understanding of Lean, really very, very basic. How many of you played the natural number game? Okay, vast majority of you have played the natural number game, so you've seen tactics like intro and have and obtain and use and things like this. That's all you need in order to do basically all of real analysis. So even if you haven't, you're not an expert on Mathlib, you're not an expert on Lean, that's perfectly fine. And the key idea that I want to experiment with, we'll see if this works, is what I call quasi-autoformalization. So autoformalization is if you just tell the computer, this is the theorem I want you to formalize, the computer spits out a perfect formalization. We're not there yet, although we're closer than I would have thought we would be at this stage. But what I have in mind is, I want to work at the level of ideas. I want to just think, you apply Cauchy-Schwarz and open the squares, and there should be cancellation. That can be converted into, informal isn't really the right word. There's a formal natural language statement that represents that idea. And then there's a formal natural language proof that represents the execution of that idea. And then, and then there should be a way to convert that natural language statement into a corresponding formal statement. And you sort of scaffold the corresponding halves and then fill them in. So, question? No, I thought I heard something. So idea is the place where I want to work. And then you can use LLMs if you don't know, well, okay, so this part you don't need the LLM to do. This was sort of a discussion about how to get closer and closer to automatic formalization. The quasi here is that at every stage a human being can intervene. A human being can be there in the middle and check if the statement really is, the natural language informal statement, really is what I mean it to be. And then if I'm happy with the statement, if I'm happy with the proof, and then have chatbot formalize that into a formal statement, and then again I have to check, do I agree that it's gotten the meaning right? And then we can try to fill in the sorries, and we get this scaffold. Okay, question? Yes, please.
I just wanted to clarify what you mean by formal natural language statement.
Yeah, so an informal statement is something like, well, this should go to 0. And then natural language formal statement is, there exists an epsilon, for all epsilon, this thing is less than epsilon epsilon. That's how I'm going to prove. How am I going to prove that it goes to 0? I'll say, you know, like let's write it out exactly as we would in a introduction to proofs course. You know, no cheating. The goal is eventually to be able to cheat, to be able to work the way we talk. You go to the Blackboard, you tell your colleague, hey, this is what's going on. You record that conversation, you upload it to a chatbot and an LLM, and it just formalizes, it writes the paper for you, right? That would be pretty nice. We're obviously nowhere near that, but we're closer than, again, I would be comfortable with. So here's the experiment. Let's see if this is going to work. My suggestion, especially for those of you who are new to Lean, is do not try to follow along on your computers. So close your computers, put them away, and just try, keep track on paper or just watch. And then we're going to do a bunch of experiments, and then at 10:30 we're going to stop with me doing it, and we'll have some tea, and then you'll do it on your own computers. Okay, does that make sense? So I think that's the best way to learn, instead of trying to type the letters. Lean is fussy about spacing. So I ran something like this at the JMM in January, and we were trying to do it all live, everyone coding at the same time, just writing the same characters that I'm writing. And first of all, they had to get Lean running on their machines, which is a pain. And then they had to, like, I went over to someone and they'd literally written everything that I wrote exactly as I wrote it. And I could not figure out for the life of me what the error message was. And it was some bizarre error message. And it turned out that instead of 4 spaces, there were 5 spaces. And that's what was ruining things. So let's not do that. Let's just follow along on paper, and after the lecture component, you'll have plenty of time to try it yourselves and experiment. Okay. Any questions, comments, criticisms? Let's go. So, right. So this is Lean. I have Lean working. It's got import Mathlib, and I'm checking that it knows that 2 + 2 is indeed 4. So this is where we give the instructions, and this is where we see the game board. Here's what you're going to do when the time comes, when we get into the breakout session. So Heather has, how are people going to find this? Is this public yet?
It is, and you can see the red link at the top. I think
Yeah. HR Macbeth/Simons 2025, if you want to write that down, or we'll come around and make sure everybody has it. There's a way, there's a link right here. If you don't have GitHub running, you just click on this button and code spaces will open. For me, I'll do it locally just because I have it. I find it useful to have Mathlib docs at the ready. So you just Google Mathlib docs, and the first link will be the documentation. So this is where we're going to check, because LLMs hallucinate names of theorems. So you want to check that, does this theorem actually exist in Mathlib? And if not, there might be some very similar name. There's at first frustrating, and then you get used to it, protocol in Mathlib where the theorem names are the content of the theorem. So you wouldn't say Cauchy-Schwarz, you would say squares, L2, LE, whatever. L1, LE, L2, L2, something like this. Okay, so it's a little frustrating, but because the names are really matching a pattern, the LLMs can learn that pattern and they can tell us what that pattern is. All right, and then the last thing that I have open, is this is Claude 4.0 Sonnet. Use GPT, use whatever your favorite app is. Now, here's the real thing I want to have open, which is Baby Rudin. Okay, so let's do some exercises out of Baby Rudin. Let's prove that the convergence of Sn implies the convergence of the absolute value of Sn. This is exercise 1 in, okay, the first 2 chapters of Baby Rudin are like, what are sets and what are real numbers? Let's jump straight to something with a little bit of content. If a sequence converges, then it's absolute value convergence. All right, let's try to state that. Now, again, instead of me just, I know how to state this in Lean, but I want to show you that you don't need to know anything about Lean by now, if you're willing, and again, that's a big if you're willing to use a chatbot like this. So tell me how to, tell me what the definition of a limit is. Tell me what the definition of a limit of a sequence is. I want to, if you remember that protocol, I want to prompt it in natural language first. I want to get into the, I want to get the LLM to be thinking about that direction. Okay, so a sequence converges to a limit L if there exists an integer. Okay, so for all n, little n greater than capital N, an is less than epsilon. Easy. Formalize this first definition in Lean 4. Here's a formalization. It's drafting an artifact. Okay, and then it's going to do all kinds of other stuff. I'm going to ignore all the other stuff. I just want to grab this, and let's put it right here. Okay, so let's read this. Everybody can see in the back. Should I make it a little bigger? Or it's okay.
A little bit bigger.
A little bit bigger. How's that?
Yeah.
One more? No, that's good. Okay, so we're going to call this definition sequential limit. I mean, you can call it whatever you want. You can call it Bob if you want. Is there a nicer thing to, how about, yeah, seq lim is or something. The limit of a sequence is L. So what's a sequence? A sequence is, for some reason, we write like, this is kind of a historical funny thing. For functions, 2 minus signs is a comment, so Lean's going to ignore what I write here. For functions, we tend to write like f of x. But for sequences, we write f sub n, right? I don't know why. That's just a historical funny thing that we write underscores. Let me make this look more like Lean. Yeah. So Lean allows you to do things like this. And I guess I shouldn't be using dollar signs, but these things so that it highlights it. Okay. Does that look a little better? So we use f parenthesis x for functions, but for sequences, for some reason, you use underscores. So in Lean, we're just going to use not, and you could put parentheses here, but they're kind of extraneous. I mean, I could put parentheses there if it makes you feel better, a of n. The point is, you do need a space. That's right. If I don't put the space there, Lean will complain. So that's right. That's right. To make it so to make it so that it doesn't confuse you when you go to use it. So this is what I mean by spaces are funny, and you might want to yeah, just take notes on paper, and then you'll see funny things with spaces. Okay, so what is a sequence? It's a map from the natural numbers to the real numbers, and then I'm claiming that the limit is this capital L. And what is it? It's what everybody knows. For all epsilon, there exists an n, so that for all little n, absolute value of an minus L is at most epsilon.
There are all sorts of spaces in there between those colons and so on. They're just as important, like a colon n to r.
No, some of them are not that important. Some of them are convention. So there's a convention that you put a space between things, and the LLM knows the Mathlib convention. But some of the spaces, well, of course, an is the word an, but if I put parentheses around an, it still is not happy. It's also, by the way, not happy if I put a space here. So you will, okay, this is what I mean by a modicum of you will appreciate you will get some experience with this, and you'll know where you can or can't put a space. And if it's complaining, you have no idea. Look at this error message. Oh, actually, expected no space before. That's a pretty good error message. You see the error message. Yeah, expected no space before, and it shows you right where it's not expecting a space. How about here? What's the error message here? Unexpected token. It expected something else, but that's not what I'm trying to say. Okay, so the error message is people are working on making better error messages. But again, you'll get very used to it. Okay, so we know what a sequence of a limit is.
You also use the subscript notation in this case, right?
You're telling me I could do this?
I'm asking you.
Oh, no, definitely not. No, subscript notation does not exist. So this was just a historical remark. Let me delete the remark, in fact. Because, okay, it's just historically, for some reason, Euler wrote f of x when it was a real valued function. If it was a sequence, Euler wrote a sub n, and we all follow Euler. So that's it. He had two different definitions of pi. Pi was 3.14. It was also 6.28 in different papers. And we just went with, in this case, one of them. And now there's a big fight over pi versus tau. Whatever.
Yeah,
Blame Euler for this.
the subscript symbol underscore n that you wrote is just another Unicode.
Yeah, it's
There's no relation with the n.
Yeah.
Although I believe like Emily Rio and collaborators working on infinity categories set up a custom posit to like translate all of those subscripts actually into the thing you're supposed to write, so they could write that, for example. So that's possible.
There are people with computer chops can do all kinds of amazing things. An idiot like me is just going to type whatever I'm told, as long as it has the meaning that I want it to have. Okay, so are we happy with the definition of a limit of a sequence? Great. Now let's think back to the exercise. Where was the exercise? The exercise was here. Why am I?
Alex, maybe one comment.
Please.
It figures out what the n is, what kind of thing.
Yes, thank you for that comment. Let me.
And the epsilon.
And the epsilon. Let me make that comment right now. Why am I getting confused with this thing? Here we are. There's the documentation. I am all over the place. Here we are. Yeah, let me make Heather's comment right now. This used to be very easy to do. Here we are. So Heather made a really good point. Here, epsilon. So let me do check. Seek lim is. And there it is. At is better. No, it's still.
Yeah, that's okay. It's shit on the line.
Well, what I want is to know what the. Oh yeah, I just hover. That's a better way.
It tells you.
But it tells me prop. It doesn't tell me what the prop is. I want to know what it thinks the definition is. But if I just hover over epsilon, you notice I never said that epsilon had to be a real number. Here it's. Let me get rid of this check. Here it's saying that n is a natural number, but actually I don't need that either. Lean will figure out. How does it know that n actually has to be a natural number? Well, it doesn't yet. It just says there's going to be some, what is n a real number? Is n topological space? Like I have no idea at the moment that, for all epsilon, there exists a topological space n or something. There's this some type, some kind of thing that I don't know. And then for all n greater than or equal to n, all right, I still don't know what it is. But then the second I say n is expecting things of type natural number. That means n must have been a natural number. That means capital N must have been a natural number. And that means this, there exists, must have been about a natural number n. So it does all of that automatically for you. You don't have to try to prescribe it. Similarly, A of n, A maps natural numbers to real numbers. So this is a real number. L is also a real number. And so this difference is in the real numbers. The absolute value is a real number. And so what should I compare it to? Real numbers. So that's how it knows that I could have meant that for all integers, epsilon greater than 0. But no, it's not an integer. It's a real number. And the reason it's a real number is because it tracked it all the way from these other places.
Can you remove the column R from the L?
I can probably remove the, apparently not. Okay.
So
Yeah.
I see why epsilon has to be a real number from what you just said. Why couldn't capital N be a real number?
So it could be a real number in the definition. I could just tell it, make capital N a real number, I think. So the way to force something to be something that, something else, Yeah, now it's complaining. And the reason it's complaining is because if capital N is a real number and it sees this, then it thinks little n is also a real number. And now the problem is A doesn't take real numbers, it only takes natural numbers.
You can
cannot
tell it.
force
So
it.
I can
force n to be an integer.
I can force n to be a natural number. For all natural numbers n, let's see.
You need an n.
Yeah, n, here's how I would have to say it. Okay, so if I want to say that capital N is a real number, then I want to make sure that little n is a natural number. So I'm saying for all natural numbers n, if n is greater than or equal to capital N, then you have this. So that's how, if you want to break out of what it's choosing automatically for those types, you can do it.
So anytime we see a comparison between two things, they have to be of the.
That's right.
Same type, integer and real number.
Comparison only exists between the same things, but we have all these coercion maps. So by the way, here, when it's comparing the n to the n.
You might want to do a print. If you do hashtag print, I think it will show you.
Is that what it is? Hashtag print? Print seek lim is. There we go. So this is really interesting. Thank you for that question, John, because now we get to see what lean is actually doing. And what it's doing is it's taking that natural number n, it wants to compare it to a real number, capital N. And what it has to do in order to do that is what this upper arrow is, which is the coercion from natural numbers to integers, to rationals, to equivalent sequences of two Cauchy sequences, equivalence classes of Cauchy sequences of rationals. And that's what that little up arrow is doing, so that it can compare a real number to a real number.
So the up arrow goes down, so to speak. This goes from natural to real.
Yeah.
It's a coercion. Well, yeah, I don't know. Yeah. Wait, depends on your orientation. Yeah.
It's like up to me.
Yeah, it's an up arrow from naturals to integers to rationals to reals. Yeah, so that's thank you for helping us make that point. And so here, if I hover over n, n is a real number because we forced it to be. Whereas if we didn't force it, why am I looking there? I can look here. Okay, here we go. If we didn't force it, then n would just be a natural number. And it's comparing, there's also a less than sign for natural numbers, and it's comparing natural numbers to natural numbers. And there's no up arrow because there's no coercion. So far, so good?
So, and the epsilon bigger than 0, this also implies it's a real number?
Yeah, that's right. Well, no, epsilon bigger than 0 by itself does not imply that it's a real number. It's the fact that here, this is a real number, and the absolute value is a real number. Now we have to compare it to a real number. But if I just say epsilon by itself,
Comment out the equality and show what happens when you're typing, when you're in the middle of typing.
oh, when I'm in the middle of typing?
Yeah, then you, for example, probably on the right, you have nothing.
Okay, I'll just call it true. I'll just call it true. In other words, it's a prop. The definition of sequential limit is a true or false statement. And I'm saying, I have a sequence. I tried to make it to natural numbers because I was going to do something else, but let me try to do what Antoine is saying. If A is a function from natural numbers, L is a real number, and it's a true or false statement. So is it true that for all epsilon greater than 0, true? It's a vacuous definition, but now let's see what it says. It has it right there. And what has it assumed about epsilon? Drum roll, please. It's a natural number. So the first thing it thinks, why is it a natural number? The first thing it thinks when it sees 0 is 0 is a natural number. If you want 0 to be a real number, I can make it a real number too, in exactly the same way. It doesn't bother putting the up arrows on numbers because it just assumes you understand that there's 0 in the naturals, there's 0 in the integers, there's 0 in the rationals, there's 0 in the reals. It does? It does put an up arrow on 0?
No,
It doesn't.
Sometimes it can.
It can for a number. Yeah, that's true.
We'll have nightmares with that.
Yeah. Okay. Are we satisfied with the definition of sequential, what it means for a sequence to have a limit L? Okay, and we came up with this definition by just talking about it and asking an LLM to write the statement for us.
It's not the initial stuff that you have.
Yeah. Oh, it's something different now? I think it's, yeah, I can do that. It's the same thing. It actually makes absolutely no difference, but now it looks exactly as we had it. We're happy with this. Okay, let's go to, I don't know why, oh, that's just something I was working on.
So let me ask
Same
one,
window as Claude.
Thanks.
one more question.
Please.
So if I understood correctly, when you write epsilon greater than 0, it assumed at that point epsilon was a natural number.
Correct.
But later it saw, wait a minute, it changed, it's able to change its mind from context later on.
Yes.
Well,
It's exact-
Not exactly.
It didn't initially assume that it was a natural number, rather it left it undetermined. And if at the end it's still undetermined, then it decides to assume it's a natural number.
The machine added that it has a constraint that there is a greater than sign between the nature of the 0. And then at the end, it observes that it can solve the matching.
So at this point, it doesn't know what epsilon is. It's sort of undetermined. It gets to here and it says, well, I don't have any more information, so I got to put something in there. I think it's a natural number. I don't have anything else, any other constraints on it, so I'll do the simplest thing I can. Yeah, and sometimes if it's not, it'll say, I don't know what you mean by epsilon greater than 0. It'll give you an error message there. Okay, great.
You should try to type for epsilon greater than A.
Greater than A?
Yeah, A.
Oh, the same A?
Yeah, the same A, so that you
Okay.
understand that there is no comparison between
Yeah, so
numbers.
So now what it's saying here, the error message that we're getting is that there's a type mismatch at epsilon. I think epsilon is supposed to be a real number. You're trying to tell me that epsilon is supposed to be compared to A is a function from naturals to reals. It's a sequence. So I don't know what you mean by, how's this supposed to work? Okay, so let's ask, let's do where's the homework? Here's the homework. So we have a sequence Sn. It converges, it doesn't specify where it converges to. So let's have that definition also. What about just a sequence converging? Do not talk about filters or anything else. Do not talk about filters. Okay, it's going to take away the filters. Thank you. Goodbye. We'll see filters later. Okay, and then converges is very simple. There exists an L so that you have so that there is a sequence limit. So I'll grab this. Well, I meant to grab a lot less than that. Here we are. I don't want this. We already have that. And then converges, is that a name we're happy with? The reason it doesn't like seek limit is because I changed the name. I changed it to seek lim is. Lim is. Okay, and then converges, how about seek conv or something? I don't know. Yeah, these are not Mathlib approved names for the definitions and theorems, since we're anyway not doing.
Like Hilbert said, you could have Planck, you could have Planck and table or whatever.
Yeah, it doesn't matter what.
Beer
Yeah,
cup.
yeah. This could be beer bottle. Definition of a beer bottle, given a sequence.
Like you did import Mathlib.
Yes.
How much of this can have been done on just on Lean without importing anything? Like would this just compile without?
So
importing anything?
the one thing that I don't think the real numbers. I don't think the real numbers. Oh, an absolute value? Really? Oh, the.
It's the absolute.
Oh, and the notation for N and R. It doesn't know what N and R are.
Here N and R are types. It's just saying.
You'd have to say nat rather than.
Right.
Okay,
So
okay.
the easy
So
thing.
there are some common notations that are already easier by just importing Mathlib. Like we can use, for example, N and R and stuff like that.
Unless you're trying to do something with Mathlib itself in which case you don't want to import all of Mathlib. You want to be very careful about importing just the right small number of things. If you just want to express yourself in some way for research or for teaching, go ahead and import all of Mathlib. There's no serious cost to it.
Yeah, I just was wondering, like, you did import Mathlib.
I did import
How much
Mathlib.
this,
It gave me the notation for N and R. I guess the real numbers are in.
You can enter hashtag min imports and you will get the minimal at the end. Hashtag
Hash min imports.
Underscore imports. And you compute.
Yeah. So as long as I import mathlib.data.real.basic.
Only one file that will import a lot of stuff, but
yeah, okay.
import a minimal.
Because if you actually go to what the real numbers are, I mean, this is another cool thing. You can right click on this and it says go to the definition of the real numbers. And you'll see real numbers are Cauchy completions of, with respect to Cauchy, of the absolute value on the rationals. What are the rationals? You go to the definition, and the rationals are an integer numerator, denominator that's not equal to 0, and the fact that the numerator and denominator coprime. And then if you say, what is an integer? I don't know what an integer is. I can right click and go to the definition. An integer is a natural number, or there it is, or the negative of a natural number. So that's -1 on down. And what is a natural number? A natural number is 0. 0 is a natural number, and the successor of a natural number is a natural number. So it's literally, when you're asking for the real numbers, all of that is in there. And that's all is sitting in core somewhere. So that's hard-coded. I mean, not hard-coded, but it's in the thing that you get just from opening Lean itself. Yeah, and there's a whole file on Cauchy sequences, exactly. Okay, so all of that is being done under the hood, but it's really, when I teach real analysis, on day one I say, you think the real numbers are this, but of course they're equivalent. I do exactly the construction we just did, and then I start proving something, and what do I draw? Right? I never again use the fact that they're actually equivalence classes of Cauchy sequences. Lean is every single time going all the way down to the axiom. For better or for worse. I mean, that's what we say we do when we do mathematics. So it's keeping us honest in that sense. Okay, let's go to the exercise. The exercise was, tell me in natural language how to prove the fact that if a sequence converges, then let's give the sequence a name. I don't know, Sn converges. Then its absolute value does too. Okay. So the key is the reverse triangle inequality. Here's the proof, yada, yada. We apply it, and okay, great. So that was just ask the LLM for the statement and the natural language proof. All of you can prove this this exercise, so I won't go through the mathematics of it. But let's see how well the LLM converts this natural language statement into a formal statement. Convert just the statement to Lean 4. Drafting artifact. Okay, great. So here's its proposed statement. I just want to copy this and go back here. All right, converges we called seek conv. I guess I should tell it what my names are so I don't have to keep doing this. But here's its proposed formalization. We have a sequence S from the natural numbers to the reals. And the way that it says to do it is seek conv S implies seek conv of the function that sends the natural number n to the absolute value of Sn. So this is how you make a function. The word fun is a special word in Lean. It means function. You give it the input and maps to the output. Okay, and so you can see the goal state here. What it knows is that there is some sequence from the naturals to the reals, a function from natural to the reals, and then we have to prove this implication P implies Q, where P is the fact that the sequence converges.
What is the
The underscore?
No, the by and the, like the end of.
Oh, the by. The by is that we're going to start the proof. So the colon equals says, okay, so let's go through the syntax. Theorem says we're going to prove a theorem. We gave that theorem a name. In fact, this is an exercise, so maybe we don't even want to name it. Maybe we just want to say example, and then we don't have to give it a name. Then what are the assumptions? The assumption, before the colon come the assumptions. So the assumption is that you have, someone has handed me a sequence from the naturals to the reals, and then the colon means here's what I want to prove. I want to prove that the convergence of the sequence S implies the convergence of the absolute value. And the way I'm going to prove this is, let's start the proof. So the start the proof is by.
Okay, so up until this point, like it says nothing because I didn't write down the proof for this example.
Correct.
Yeah, okay.
And the reason it's not giving us an error message is because we're telling it, sorry, I know I didn't prove it yet. Don't give me an error message. If I take out,
okay.
sorry says, don't give me an error message. So now it says, you know, you stopped, but you didn't prove it. What's going on? I thought we're friends here.
Then I
Right?
can work on it. Sorry, somewhere.
Right.
I can like, okay.
So you say, I know I didn't prove it yet. Just, you know, hear me out. I'll get there. Okay, so that's what the sorry does. It takes away that one error message. Without the sorry, everything will still go. It'll just give you an annoying red underscore that says you didn't do it yet. I know I didn't do it yet. Let's work anyway.
That will work everywhere, anywhere, like even in a definition, if I write sorry, it will just drop the.
So it doesn't know, you know, you haven't told me what the prop is. What's the prop? What's the definition? I haven't told it to you yet. Sorry, I'll tell you the definition later.
Okay.
And it says, okay, fine. Well, there's a yellow squiggly underscore that says, you know, the declaration uses sorry. So you didn't finish telling me what this definition is, but I'll let you keep going. Okay. So that's what sorry does.
You can use the definition with a sorry in the rest of it.
Yeah. Yeah, you can do, in fact, we probably won't have time to do another exercise, but there's another exercise which is calculate the limit. In fact, I'll try to at least state this one at the end so you can see how you might formalize, calculate the limit if we don't know the answer yet. So there's a way to do it. Okay, first let's get through this exercise. So let me go back to Claude and I'll say, okay, now scaffold, now use our natural language proof as a scaffold for a formal proof, leaving sorries where needed. Let's see how this works. This is all experimental, so we'll find out what it does. Okay, so here's the proof that it's giving us. It's sort of writing a bunch of stuff, then it talks to itself and says, whoops, that's not what I want. Okay, so here's what it says is a proof. I'm going to copy all of this. Why can't I select? There we go. Because it's going to have its own names for it. I think it's not really going to use the names. Okay, so this is nearly one shot. It is almost a perfect proof. There's one thing wrong, and I know what's wrong. Let me fix what's wrong first so that we don't have this error message, and then we can go through the proof. What's wrong is that the way that it does the absolute value, it can't have an absolute value next to an absolute value. You need a parenthesis here so that it stops complaining, and same thing on this side. I think that's all we need. And now it has a nearly complete proof. Okay, so what's the proof? Let's see the game board. Let's see the game board at each step. So again, the game board at this point is that we have a sequence, and then we want to prove if the sequence converges, then so does its absolute value. The first step is intro LHL. So what does that do when you do that? It introduced the fact that the sequence converges actually two pieces of information. I mean, it's really slick. It did it a little faster than I would have done it pedagogically. But the first thing it does is it says that it knows what the definition of C-conv is. Let's do it slightly slower. First, I want to intro, I'll just call it H. Intro H, and let me exit out so that I don't get errors below, and sorry. Okay, so intro H is I introduce the hypothesis that S converges. Maybe I should give it a better name than H. Let's call it S converges. Okay, but what does it mean to converge? I've forgotten the definition. Let's unfold the definition of seek conv at S conv. Okay, just to show you the kinds of things you can do. So the previous goal state was this. So I said, let me go to the beginning of line 14. So if I have P implies Q, if you're trying to prove P implies Q, the first thing you should say is, okay, so give me P, and then I'm going to try to prove Q. So intro says, give me P, give me the fact that the sequence S converges. So now we have two things, and we're trying to prove that the sequence absolute value also converges. Then I'm saying, I've forgotten the definition. Lean knows the definition, but I've forgotten the definition of sequential convergence. So where it says S conv, could you just replace that by its definition? And the definition is there exists an L so that this holds. By the way, there's also seek conv at the goal, and I've forgotten what that is. So let's also unfold the definition seek conv at the goal. And now I can see things in slightly easier form. So I know that there's a sequence S. I know that there's a real number L so that S converges to L. And what I want is to find some other real number L, also called L. That's, that happens, but those are different L's, of course, so that the absolute value converges to L. Okay, so you can see all those things, and Lean can see all those things. Now, what it did is it jumped straight to, so the fact that there exists an L, it jumped straight to give me that L and give me the hypothesis on L. So instead of doing everything that we did, am I going too fast? Please stop me at any point if I'm not clear.
The difference between line 15 and 16.
Okay, so what happened between line 15 and 16? You can see Lean is in red showing you what the line is about to take away, and in green showing you what it replaced it with. So between line 15 and line 16, all that happened is the definition of seek conv was unfolded.
But the difference between 15 and 16.
The difference between 15 and 16 is, the difference between what I've written at line 15 and line 16?
I see the difference. It's written at S-conv at the end.
Yes.
This is actually happening under the hood. That's what I want to understand.
So what's happening under the hood, when we're at line 14, I have two things here that use seek conv. And line 15 says at S-conv is this statement, unfold the definition seek conv. Line 16 says there's also seek conv in the goal. So if I want to do something at the goal, I don't have to say at the goal. It just knows that this by default is doing something at the goal.
Perfect. Thanks.
And in fact, I can do both in one fell swoop by saying S-conv and also goal. And now in one fell swoop, it unfolded both. You can even do unfold it wherever you see it. Whoops. If you just put a star, that means unfold it wherever you see. I just don't remember what sequence convergence is. Could you please, anywhere you see seek conv, replace it by its definition?
Okay, perfect. And another question, like you wrote introduce S-conv. Like, why did it automatically knew like what you mean by that? Like,
So S-conv is just a name. I could have introduced Bob.
was it type of something? Why did it know that now?
The goal is P implies Q. So in order to prove P implies Q, give me P, and now I have to prove Q.
So introduce is just give me the hypothesis.
Give me the hypothesis. Yeah, there are more hypotheses I can pull out. Okay, so introduce Bob.
Right now, when you just said intro Bob,
Yes.
This does not know what Bob is.
Well, the way that it figured out what Bob is that it knows that the goal is P implies Q. So
I see. So this line also just tells you let Bob be the.
Let Bob be this thing and assume that it's true, and now our goal is to prove this. So that's what intro. Introduce the fact that, should I call it P?
No, Bob is good.
Bob was good. Let's keep Bob. We like Bob. Right? There's nothing special about the word S-conv. I just like my hypotheses to represent what they represent, so I don't have to think about was that hypothesis 3 or hypothesis 7 or hypothesis underscore? Like, what did I call that thing? In the same way, the theorem names are named after the thing that they represent.
N. You can call it N, and then you will be confused.
I can call it N, and then I'll be very confused when it comes time to use capital N for something else. Yeah. Okay. So Bob it is. Okay. So far, so good. So what Lean has done is what the LLM has done is in one fell swoop, it took this introduction step and broke down, it knows what sequential convergence is, that there exists an L so that the sequence converges to L. And in one fell swoop, just got both of those things.
So
Okay.
we somehow took L, and now this is genuinely the limit.
Yes, but again, L is our name for L. We could call this whatever.
I
Bob.
understand that that's like, I don't care what the name is.
Yeah.
It somehow both gave us the real number that we care about and also just the hypothesis.
The reason is it knows what sequential convergence is, and sequential convergence is a pair of things. It's a real number L together with the fact that A converges to L.
Okay,
So when we said intro this thing, we can intro that pair of things all at once. And when we do, we'll get the real number Bob and the fact that we've called HL that S converges to Bob. Okay, so it did that in one step.
And HL is just a name, right?
It's just a name.
Call it Ida or something like that.
Ida? Ida is the fact that S converges to Bob. You want to give names to facts so you can refer to them. John, you were? Yeah. Go ahead.
What role do the angle brackets play?
The angle bracket is that seq_conv rather. Seq_conv is a pair of things. The definition of seq_conv is there exists an L and A goes to L. So it, in one fell swoop, got the L, which we called Bob, and the fact that S goes to Bob, which we called Ida.
So if you leave off the angle brackets, though.
If you leave off the angle brackets, so instead of this, we could just introduce P, and then it'll be one thing, and then we have to obtain. So this is the slower way. So let me do it the slower way as well. Unfold seq_conv at P. So now we know that there's this pair of things, and then let's obtain that pair of things. Obtain Bob, comma, Ida from P. And that will accomplish the same thing. So obtain is the way, if you have something that says there exists, P is the fact that there exists an L so that S goes to L. Obtain is the way that you get to that L and that fact. But we called it Bob and Ida. Okay, so that's the first step. So far, so good. Let me unfold the definition again of seq_conv just so we can stare at it. So what we're trying to prove is that there exists some L. We have an L. We called it Bob, and we want to show that there exists an L. So what L should we use? The absolute value. And look at what the LLM said for the next step. The next step is to use absolute value of L. Okay, so let's use absolute value of L. Except L was called Bob.
What does use?
Use, if you have if you're trying to prove that there exists an L, you have to give it that value. So which value should you use?
So when there is an exists claim, I can use
Goal,
the
yeah.
use.
Use is the tactic that when you tell it, that's the thing that you want to use for L. And so
There are multiple exist signs. Can you still use?
yeah, you can use for one of them, use for another one. Yeah.
Should you indicate which use?
No, because it's the first one, whichever one comes first. Yeah. So if there exists an L and there exists a K and there exists a Bob, then the first use we'll put in this one. And then, yeah, please, thank you. That's perfect. That's perfect. So if you have what Heather's writing is, if you have a hypothesis that has there exists on it, you obtain the thing that the hypothesis says there exists. And if you're trying to prove that there exists something, you have to give it the thing that you're trying to use. Okay, so we're going to use Bob, and now our proof, the thing that we're trying to prove is that the limit of the sequence that sends n to the absolute value of S is the absolute value of Bob. Question?
Sorry, I have a question about the Knuth. Why is intro under goal and not hypothesis? Because we use that to get the hypothesis, right?
So let's go back to here. Our goal has an implication in it. So if P implies Q is the goal,
Right.
then when we use intro at the goal, it will take this and add it to the hypothesis.
So I guess you're asking why I wrote the table in the way that I did, and I'm
Yeah, I
saying
guess so.
the presence of that logical symbol in the goal suggests the use of
Got
that.
Got it. Okay. I understand what the table's doing.
Yeah.
Yeah. Great. So we're going to use Bob. And then what is the definition of sequential limit? So I forgot what that definition is. So let's unfold seq lim is at everywhere, because I don't remember what that is. So IDA turned into for all epsilon there exists an n, so that Sn minus Bob is at most epsilon. And what we're trying to prove is for all epsilon there exists an n, so that for all n, the absolute value minus Bob minus the absolute value of Bob, because that's what we, that's the L that we told it to use is the absolute value of Bob is less than epsilon.
Could have we given the function from n to the absolute value of S of n a nicer, like, have we compressed it to something which is easier to read? Like,
so tell me if this is easier to read. Is it dot? What am I doing
No,
wrong?
you need parentheses. You need parentheses
I need parentheses on the
around
dot.
the S as well.
Around the S.
And like
All the way?
joint parentheses around the S and the dot. No internal.
I don't remember what the, so this is where you would ask an LLM, what's the syntax if you want to write it in a simpler way. Absolute value of Sn. There we are.
it's mainly for readability I'm asking, right? Like somehow,
Wait, there we go. Mainly for readability. Yeah, so
you would call this function G or something, like you're defining another sequence out of S. I would just give it a name. Usually when I write the proof, I'm asking.
Sure. Oh, yeah.
Are you giving it just a name and
Sure.
use this name?
So let's do set t, which is a new function from the naturals to the reals, and we'll make it the function that maps n maps to absolute value of Sn. And the fact that I put set means it's going to look anywhere in here, wherever we saw a function from the naturals, it turned it into t. And it remembers that we now have a function t that is the function that sends n to the absolute value of s. We also, before we used absolute value of Bob, maybe it's not nice to see the absolute value of Bob, we can let L be absolute value of Bob and then use L if you prefer. And now it's slightly nicer at the cost of a few more hypotheses.
Yeah,
but
that's just how I used to write proofs.
Yeah,
when I write
beautiful.
it down, right?
Yeah. The whole goal of this lecture is that you can be as expressive with lean as you want to be. However you want to say things, you should be able to say it that way in a formal system.
So let and set basically do the same thing, except that set also makes these replacements.
Exactly. Yeah, exactly. At this point, there was no absolute value of Bob anywhere, so set would have done nothing different from let. Whereas at this point, if I only let, it would make a new definition, but it wouldn't go and look for that definition somewhere else. So that's where a set helps come in. Again, you're going to pick up all of these things as you get a little bit of experience with play. And I want to make sure we have time to play. So let me keep an eye. Okay, I'm 1 minute over. So let's just finish the proof by seeing what it does. So what are you going to do with an for all epsilon positive? What do you do with a for all? Introduce, yeah, introduce the epsilon. So introduce the epsilon and introduce the fact that epsilon is positive. So we can call that, I don't know, eps pos or something. It's up to us to name it. So now instead of saying for all epsilon positive, at the end of the line, we have epsilon's a real number, epsilon's positive, and now we want to show that there exists an n. Okay, where are we supposed to get that n from? IDA. IDA says if you give me an epsilon and a proof that epsilon is positive, I'll give you an n. Okay, so what should we use? Use IDA when you feed into IDA and epsilon and the fact that epsilon is positive. That should be the same n, dot 1. So let's see. Let's have, just to see what this statement is. So have is I want to make a new statement. Let's have that statement. The statement, because I didn't give it a name, its default name is this. There exists an n for all n greater than n. This difference is less than epsilon. Okay, and then we have a hypothesis that there exists an n. So what can we use how do we obtain that n? I gave it away. Obtain that n and the hypothesis on n from this. Okay, so now we have a capital N and we have this hypothesis on n. And I'm sure that's down here. Yeah, it's right here. Obtain the n and the hypothesis on n from ida, epsilon, and so on. So let me, I don't know, should we keep going with this proof? You want to take, we're a little bit over time, but let's just finish it and then, yeah. So we'll use, sorry?
Let's finish it slowly.
Finish it slowly. Yeah, okay, please. Yeah, so far so good?
Yeah.
Okay, so far so good. So let me hide that. What n should we use?
From this.
The n that we just got, which is sitting right there. So we'll use that n. Let's use that n. Okay, so we've used that n. Now our goal has changed to for all n greater than n. What do we do with how do we make progress when there's a for all statement? Intro. So give me the n, intro little n, and then there's an implication. So also give me the fact that little n is greater than capital N. We can call that whatever we want. Let's call it n greater than capital N. So now we have two facts. We have n greater than capital N. We have a natural number n, and we have the fact that n is greater than capital N. And we're trying to prove that the absolute value of t minus L is less than epsilon.
Why don't we use angle brackets here?
Angle bracket.
Intro and greater than.
Because they're two different things. So that's a really great question. The P I can try, but it's not going to. The seq conv is a package of two different things that are coupled together. There exists an L so that something happens. So that's why they would be coupled like this. Whereas here, I realize that it might look like they're coupled, but they're actually not coupled. There's two different things. There's a for all natural numbers n, if you can give me a proof that n is greater than or equal to n, capital N, then we continue. So it's like an implication. If I put the angle brackets there, it'll complain because that's just not the structure that's there. Invalid constructor, you're trying to break up, it's trying to see one thing, and the one thing it wants to see is the natural number n, and I'm giving it a pair with the natural number n and it doesn't know what to do. So I can break it up into two lines if that'll make it a little better. So the first intro just gives me the natural number n, and then we have a p implies q. And p is little n is greater than or equal to capital N.
So it gets what the meaning for n greater than or equal to capital N from where you are in the argument.
Exactly.
It looks at the hypothesis.
It looks at the hypothesis, it sees p implies q. So now I need to intro p. So far, so good? Okay. So we're almost there. Now we haven't done any math, right? There has been zero mathematics yet. We haven't had a thought. There's no idea. There's one idea in this proof, which is how do you actually prove that the absolute value, remember what T of n is. T of n is the absolute value of S of n, and L is the absolute value of Bob. So how do you actually prove this? And it knows that there's one place where it has to use an idea. So let's copy this half. This is a good half. Let's remember that Sn minus, we don't call it L, we call it Bob, is less than epsilon. And the reason is ida of n and not hn, but n is greater than or equal to n.
It's a H capital N, not.
I'm sorry, H capital N. Oh, H, not ida, H capital N, thank you. And then n is greater than or equal to n. Okay, so let's just think about this. H capital N is the fact that if you give me a natural number and a proof that that natural number is greater than or equal to n, I'll give you the fact that Sn minus Bob is less than epsilon. So we'll give it a name this time. Instead of calling it this, which is the default name, we'll give it an actual name, H1, which is that Sn minus Bob is less than epsilon. How? You take Hn, it's waiting for a natural number n, you feed it little n, now it's waiting for a proof that little n is greater than capital N, you feed it that hypothesis, and now it comes up with what it was supposed to. Okay, so that's H1.
And maybe you don't need to type
You do not need the type of annotation. That was just for us to be able to see what H1 was going to be. But Lean knows what that is. Lean knows the answer. The type. I'll leave the type annotation just so that we can still remember what the statement of H1 is without having to look at the game board, just looking at the moves.
Why do you have to say have H1? Does it know you have H1?
So what it knows at this point is the fact that if you give me any number greater than n, and in other applications it'll be you know, I need to go farther out than just like the squeeze theorem or some other theorems that you can prove. You'll have to do something more to prove that little n is greater than capital N. In this case, we can use the same little n as the one that we had for the original sequence. So this is a statement which is an implication. If you give me a natural number and you give me a proof that n is greater than capital N, I'll give you this. I have a natural number and I have the proof that n is greater than equal to capital N. So if I feed these two things into this, it'll spit out this fact. But I want to have this fact separately for whatever reason. I want to have access to it, and so that's what this have is doing.
So it doesn't do the logic of putting those three facts together.
Unless you tell it to. So when you tell it to put those three facts together, then it does the logic. But you have to tell it those three facts. Because again, in other applications, the three facts that you have to put together are not immediate from the facts that you already have. So you might have to do something before you can.
15 facts and it wouldn't know which three to combine.
Exactly. Okay. And then H2, so this is the one place where we're going to do something not entirely trivial. This is the one place where there's mathematics. Let's see. It's the fact that absolute value of Sn, which we have another name for, right? Our absolute value of Sn is T of n. And then we don't need these parentheses. And then absolute value of L, we also called something. Oh, that is L. Thank you. Is bounded by Sn minus Bob. You chose these names, not me. You can't complain. Okay. And I don't know how to prove this. This is the one place where we have something non-trivial happening, which is that the absolute value function is Lipschitz with constant 1 or something. Right? Like there's something to prove here. That the absolute value of Sn minus the absolute value of Bob is less than Sn minus Bob. If you allow me that fact, I will not prove that fact for you. There's a sorry. But if you allow me that fact, let's see how to finish the proof. Well, then we're done. And the proof is just use linear arithmetic between the things that we already have. Come on, figure it out. I told you that Tn minus L is bounded by Sn minus Bob, and I told you that Sn minus Bob is bounded by epsilon. I'm trying to prove that Tn minus L is bounded by epsilon. Figure it out. Now, if you didn't want to use automation, if you didn't want to use linearith, let's see. Don't use linearith, or give me a calc block instead. Okay, just to give you some other way that you could do it. Instead of automation, it reached for automation, which is the right thing to do, but just pedagogically, it took away the linearith and then give me the calc block so that you can see that you can do a calculation like this. No, don't explain, just let me copy it. And then we're going to get some t. So if I don't do the linearith step, and I do the calc block step, again, it's going to complain. Let me make this a Tn, and then it won't complain. This will be L, and then this is Sn minus Bob. And that fact is hypothesis 2, and this fact is hypothesis 1. So what's happening here, just to make it a little bit clearer, maybe that's better. Why doesn't it like it? I just want to tab it over a little. By exact. Okay. So sometimes it has some fun.
Because look at Tn and it's the same.
It's the same. I don't know. Yeah, it's sometimes calc blocks are sometimes a little fiddly, but the point is at this point I want to chain these things, so I'll do a calculation. Tn minus L is less than or equal to Sn minus Bob. Why? Because of H2. And then that thing, that's what the underscore is that thing is less than epsilon. Why is that true? Because of H1, and that's what we wanted to prove. That's the end of the proof. Okay.
That's very cool. The column equality is the same as like we doing a calculation on the right and just write because of whatever we.
Very smart people worked very, very hard so that idiots like me can look at this and understand what's going on. Okay, that's exactly the point, is so that it looks like math. So there's no difference between this and that. Okay, there's only one thing to prove, and then we're done. Fill in the sorry, find a theorem in Mathlib that does it. So this is where we need the library. This is the one place, I think, so far, other than the fact that we have real numbers and inequalities and so on. This is the one place. Okay, it found it. Abs, sub, LE, abs, sub. I warned you. Okay. Okay, so this is it. This is exactly it. Now, let's see if it made that name up or if it really exists. It really exists. So this is a documentation page. Here it is. In any additive commutative group that has a linear order, and which is an ordered additive monoid, whatever, for any pair of elements, you have the reverse inequality on the absolute values. In complete generality, that's the name. And let's read the name. The absolute value of the absolute value minus the absolute value, abs sub abs, is less or equal to abs sub. Okay, so that's why the LLM could guess it. Yes.
Couldn't have two absolute values.
I don't know why it's not breaking here and it is breaking there. Actually, let's.
Because it's printed out. It's not.
It's not actually.
The documentation prints something that you can't read.
It does have a parenthesis in between.
Oh, good.
But the way the documentation prints it is better than the way that you have to write it in Lean.
You'll fall into the trap many times.
So I'm just going to copy this theorem, and then here we are. So I'm going to fill this one sorry with 2 underscores because I don't want to. This theorem takes 2 values, and I'm saying I shouldn't have to tell you what those 2 values are. Figure it out. What is A and what is B in that theorem? It figured it out, and that is a sorry-free proof of exercise 1 of Baby Rudin. I need to delete the sorry because don't be sorry. There's nothing to be sorry about. Okay.
You have a tada. No, you don't have a tada.
There's no goals. No goals. Yeah.
Yeah, but the example, you have a symbol that it is false.
Yeah. The double check mark. Okay. We solved the example. So okay. We have coffee, tea, cookies. I don't know. Something's out there. Here's my suggestion to you for what to do for the next hour. Repeat this experiment on your own.
We need to show the installation.
For those who want Lean installed on your computer, you're welcome to. For those who don't, you just go to wherever we were here. If you find you want to write this link, it's github.com/hrmacbeth/Simons2025. And you just click on this button. If you have a GitHub account, you need to make a GitHub account if you don't already have one. And you click on this and then just play. The goal is to play. There's nothing particularly.
I installed Lean a while ago, but I'm not sure if Mathlib. Like, does it come automatically, or does you need to pull it first?
We'll circulate around and help anyone who wants help with that. But let's get some cookies.